Flipped classroom video for Maths AS Unit 1, Vector Problem Solving. So in looking at problem solving, we very often use what are called position vectors. And what are these and why do we use them? Well, the vectors we've been dealing with are not fixed in a particular place in space, and they can be called non-localized vectors. But sometimes we want or need to specify where a vector quantity is acting. And a good example of this is if we have a force, which is a vector, and it's acting on an object, then generally we need to know at what point it's acting, so it's positioned in space. So often we use an origin, O, and O generally stands for 0, 0 in 2 dimensions or 0, 0, 0 in 3 dimensions, and other points, so for example A, B, C, and we can use them to define vectors. So if we have these points here, then we might then call the vector defined by how we would get from O to A as OA. So notice that's become bolded because it's a vector now, and we might call that just little a, again bolded, and the vector from O to B would be B, and so on, and these are known as position vectors. So we can see there we're going from O to A, and that's called little a, and O to B, and that's called little b. And the rules that we've looked at previously still work with position vectors. Okay, so vectors between points. How can we express A, B? And this is useful because in a geometrical situation we may want to know what the vector AB is in order to solve some sort of problem. So what we can do is we can think about how do we travel from A to B. Well, we can travel via O. And what that means in a vector sense is that to get from A to B, we go from A to O, and then we go from O to B. And that looks like this. So the green AB would be the sort of direct A to B, but we can just as well do that by going along from A to O and then from O to B. Now what that means is that to get from A to O we're actually doing minus A, because we're doing the length of A but in the opposite direction, starting from big A, so that's minus A. Once we're at O we just have to add B on, or do B, and we get to capital B. And because we already know that we can swap round vectors when we're adding, we can write that instead as B plus minus A or B minus A. And we can see that on this diagram that if we start at A and travel along B and then minus A, we do of course get to capital B, and that's a good example of the practical use of the vector parallelogram when sort of visualizing what's going on. So that's how we get the vector AB. So AB is equal to B minus A, and that's true for any old points. If we had PQ, that would be Q minus P, and so on. So we often want to find a midpoint in geometrical situations, and we can find the midpoint of a line using vectors. So here are 3 points, O, A and B, and if we think of the midpoint of AB, which we're going to call M, as being halfway along AB, which of course it is, then if we want to get from O to M, then first we would go from O to A, and then we would go from A to M. And that means O to M is OA plus AM. And you may want to use the dots we've got on the screen to do a diagram for yourself as we work through this. Now, what we know is that to get from A to M, that means half of going from A to B. So that means AM must be a half AB. And we can sub that back in the previous equation, so OM is now equal to OA plus a half AB. So if we use little m to stand for OM, just like we do for the little a for O to A and little b for O to B, then that gives us that m is equal to A, which is of course the vector OA, plus a half of B minus A. We can open up the bracket, so that gives us A plus a half B minus a half A, and we can see then that we've got A minus a half A, which is just a half A. So now we have a half A plus a half B, and we can take the half out and make a bracket, so that gives us a half A plus B, which is a pretty cool result and so much easier than doing it using trigonometry or other forms of geometry, or even drawing a scale diagram, because that tells us where m is in a really nice and simple way, and we can see some of the benefits of vectors coming out in these sort of problems. And I said pretty cool result, and there it says pretty cool result. So let's have a look at what that looks like. Well, we've got our m halfway along as we had before, but now with the vectors on, we can see that to get from O to m, we can travel along the vector m, but the end result is the same if we were to go all the way along vector A and then halfway along the vector from A to B, which is of course B minus A, and that would take us to m as well. And to see it in terms of the result, then we can see that if we went halfway along A, so from O to the midpoint of OA, that would be the A over 2 or half A, and then the dotted blue vector B over 2 would then take us to M. And if we did it the other way around, if we travelled along B, halfway along B, so that would be half B, and then did the dotted red vector, which is half of A, again of course that would take us to M. So we can see it all shown there. Now the last thing in this video is pretty hard, as it says on the screen. And what we've got here is we've got O, A and B again, and we've shown their vectors. And we have a point P which is somewhere on the line AB. And what we are told is that the distance from A to P and the distance from P to B are in a ratio which is lambda to mu. And of course lambda and mu just stand for numbers, but with them not being numbers it makes it feel a bit more difficult, but in the end they are just representing numbers. So what that's telling us is we know how P splits the length of the line AB. And we're going to define the vector from O to P as we normally do with these, as you're getting used to now hopefully, as little p. And we want to find what that vector is in terms of what we already know. So what do we know? We know the vector A, we know the vector B, and we know about lambda and mu. So the first thing is we want to put lambda and mu onto the diagram so we can have a view of how it looks. And the length AP is some multiple of lambda, and because the length PB is in that lambda to mu ratio, that will be the same constant times mu. So we can say k, which is an arbitrary constant, times lambda for the length of AP, and k times mu for the length of PB. So we can multiply numbers. Mu, k and lambda are all just numbers, and of course we can change the order of numbers because we can multiply in any order. So we have mu times k lambda equals lambda times k mu. And that of course means we've got mu times AP, and now notice that's AP not in bold, not underlined, so that means the length AP, and that is indeed k lambda, and then we have the length PB, which is k mu. Now because AP and PB are in the same direction, then that means we can say that mu times the vector AP is equal to lambda times the vector PB. Now once we know that, we now think about where the vector little p comes in, and what we want to do is to represent AP and PB vectors as we've just used in the bottom line of the red writing and turn them into expressions using the vectors we know about and the one we want. So we know about A and B and we want P. So the vector AP would be P minus A, as we've seen previously, and the vector PB will be B minus P. And if we then put those versions into the line above, then we get mu times P minus A equals lambda times B minus P. And we can get rid of the brackets, so that's mu P minus mu A is equal to lambda B minus lambda P. We can then add lambda P to both sides and add mu A to both sides, so effectively moving them across. And that means we have mu plus lambda times P on the left hand side, and we have lambda B, which we already had, and then plus mu A from the other side. And now we can express P, because we can just divide by mu plus lambda, because it's just a number. And so we get the expression lambda B plus mu A divided by mu plus lambda. And that is often written with the A and the B in alphabetical order. And the key thing to remember is that although the ratio was lambda to mu, in this fraction the mu and the lambda swap round on the top, so we have mu A plus lambda B over mu plus lambda. Now that's all very general, and if you've struggled with that, that's because it's difficult, and you may well have to look at it again with your teacher possibly, but if you take it carefully you'll probably get a good grip on it. But a good way to sort of help make sense of it is to look at a numerical example. So if P were to be a third of the way along AB, then that would mean that we could allow lambda to be 1 and mu to be 2. And that would be splitting AB into two parts, one of which was length 1 and the other was length 2, or proportional to length 1 and proportional to length 2, which would mean that P was a third of the way along. And if we use those numbers and pop them into our formula, then P would be B plus 2A over 1 plus 2, and we could rearrange that so that it ended up as P is 2/3 of A plus 1/3 of B. And if we look at the diagram, which roughly represents that ratio of 1 to 2, does it make sense? If we imagine travelling 2/3 of the way along A, and then doing the vector, which would be the same as 1/3 of B, does that take us to P? And it sort of does make sense. We can see that that makes sense. And if we did it the other way round, if we travelled 1/3 of the way along the blue vector B, and then did a 2/3 of A going up from there, then that would get to P. So we can see that this works in a rough way. Obviously we're just looking at a diagram, but you could play with this on Desmos or GeoGebra and see how it works that way.